Alright, hey everybody. So last night I did a talk at GR Dev Night, which is a little development meetup in Grand Rapids, Michigan. And the quality of the video wasn't that great, so I thought while it's still fresh in my mind, I would go ahead and do a re-recording of it. So this is a talk on why build an engine from scratch. It's kind of our journey, OpenFX Entertainment. Kirk Rohrig and I put this together, and it's kind of what our process was of going through and building out an engine and why we even bothered to in the first place. So to get started, here's some quick overview information. I'm Garrett Hoofman. That's my Twitter handle. Got Kirk Rohrig and his Twitter handle, and then GR Dev Night sponsored the event last night, and they'd be a great one to follow as well. All right, so let's start with why you shouldn't build a game engine. First of all, it's extremely time consuming. You're gonna find bugs galore. You'll find everything. And on top of that, you probably don't have the skill set yet, or even the desire to gain the skill set to do it. But then there are so many engines already available, and there's probably one that's already specifically designed for you. You want to build a platformer? There are engines specifically for platformers, for first-person shooters, for racing games, flight simulators. You name it, there's an engine for it. So the question really comes down to why wouldn't you use one of these? I mean, you've got a huge variation of possibilities to use, so why not just pick one of them? So Unity, this was about 2 years ago when we decided to go ahead and build our engine. And Unity was just coming into the mainstream. And it's definitely not as big as it is now, but still getting there. And Unity's a good idea, especially for getting started, but you can't get the source code for Unity, at least not very easily. You can contact them and maybe you can get it. Unreal's another good choice. I mean, they're hosted on GitHub. You can actually get source code for the Unreal Engine. But then you've got 5% of your revenue right off the top that you have to give them. Monogame, Ogre 3D, both open source projects. They do pretty well, but they're not the fastest. I mean, Monogame is using C#, so you got kind of a scripting language thing. You're not quite as low level. Ogre 3D does C++, but it's not the best for performance code. So why would you ever want to then? You've got all these engines, tons of possibilities, so learning and a challenge. Those are probably the biggest reasons that we decided to go ahead and create our engine for. You learn a lot. I mean, from input systems to audio, physics. You touch the whole thing at some point or another. And speed and performance was the next big thing. We took the idea of data-oriented design to an extreme. So then we could start pushing the ones and zeros through the processor and memory as fast as we could. And we'll get to that here in a minute. And on top of that, sky's the limit. So you can do anything. Like right now, this presentation is running off of our engine. We're calling it the OpenFX, the OP engine. And this is running off of a Node.js add-on, which is running our engine. And then I actually have an app that's hosting out an AngularJS app through Express, so I can control the presentation and go back and forth. So really, the sky's the limit. You can imagine it. C++, you can do it. So that's the next big thing, is choosing our language. So we sat down and we needed to decide what we were going to do. And trying to figure this out, we had just come off of an XNA game. And XNA at the time was already dying, but Microsoft was really just, they're done. So we knew we didn't want to keep going with XNA. And so we sat down for a good 2-3 nights of battling back and forth whether we were going to do this or that, do a C# SlimDX type thing, or do an actual C++ engine, or any of these things. So, and it had to use these APIs that we needed. We could do OpenGL, DirectX, and OpenGL, you can do almost all the platforms. And then you got audio. So we did a ton of research and came up with a conclusion of these things that we wanted to use. So we started looking at the languages, and Java is one that pretty much everybody knows. I mean, it runs on pretty much all of the devices that you would want, but it's got its drawbacks. And it's kind of slow, and it's not the slowest language ever, but it's definitely not fast. The IDE choices, I could just be personal preference, but I don't like Eclipse. And then operator overloads aren't there in Java, so you can't do like vector A plus vector B equals vector C without having to do method calls, which we'll get into why method calls are not that great either. So the next obvious choice was C++, and that's the biggest known language for game developers right now. Pretty much any game studio that does lower level stuff is going to do C++. And most devices will run it. There's hardly any devices that you can find that won't run some kind of C++ or get to it somehow. But C++ is a little bit more complex. Nobody is an expert in C++. No matter how many years you spend into it, you're never going to master it. And it's not the prettiest of languages. I mean, you got these pointers and functions and everything, and especially when you start getting into templates and the whole boost library and everything, things start to get a little bit messier and harder to understand. So what we had ended up deciding was to do C and a very minimal subset of C++. So C++ brought operator overloads, so we can do our vector A plus vector B very easily. It's still got the memory management, so we got pointers, which is good for data-oriented design. And we're going to cover that here in just a minute too. And it works the same way that a computer does. C is basically just readable assembly. And it makes it so much easier to try to step through exactly what the computer is supposed to be doing with your code. Alright, so we figured out that we wanted to do C++. And then we wanted to be able to build on all these platforms. We got Linux and OS X and Windows. We didn't want to get locked down to Windows still. That's what we were doing with X and A, and it's not the best, especially when you've got all these people, especially with as big as OS X that you can get in. So we ended up choosing Cmake as a build tool. And all that does is it'll generate your solution. So then, if you're on Windows and you're wanting to use Visual Studio, you can use Cmake and it'll build out a Visual Studio solution for you. Versus if you're on OS X, you could build out an Xcode project. Or in Linux, you can make a Make project. And it'll just build it out. And the cool thing about that is that it'll separate your source code files with your solution files. And when you start checking that stuff into Git or SVN or whatever you're using, it cleans that up a lot because you don't have a whole bunch of conflicting files. So then our main idea is we wanted this to be super multi-platform. So we wanted to hit mobile devices. And this was when the UI was starting to come out, and we decided we wanted to hit that. And so wanting to use C++, the Android NDK was the obvious thing. And really, you're not going to get any performance gains by using C++ on Android, but you will get to reuse the code. Unfortunately, the NDK is highly frustrating. If it works the way you want it to, it's great, but as soon as something goofy you need to do, it's so frustrating. Alright, so the next thing, we wanted to do a data-oriented design approach for the engine. And I found that most people have never even heard of data-oriented design. They've only heard of object-oriented design, which is the whole polymorphism, like a sheep is an animal, a dog is an animal, so you've got class hierarchy type thing. So a data-oriented design takes a little bit of a different approach, and so I wanted to create kind of an analogy for this. So we're going to assume that you've got a chef, and your chef is your CPU. He's the guy that you're going to give him stuff, and he's going to chop things up in pieces and make you a meal. So this is going to be based on Intel i7 processor, which has 4 cores. So it's kind of like you've got 4 different chefs. And we're going to say that anything that's on the table for the chef is going to be the registers for the CPU, something that he's already working with. So kind of like a salt and pepper here, he's just got it and you can start using it immediately. Then you've got your L1 cache, which we're going to say is this chest here in front of each one of the cores. And your L1 cache has got, for the i7, 64 kilobytes of memory, but it splits it out into 32 kilobyte blocks. So you got 32 kilobytes for memory and then 32 kilobytes for the instruction sets. And then after that, you've got L2 cache. It's quite a bit bigger, but it's a little bit, takes a little longer, and we'll get to that in a second. And then after that, you have L3 cache, kind of like a giant pantry. So you got tons of stuff that you can put in there, but it's a bit further away. And then even further out, you got your main memory. And that's even further out, but stores a ton of stuff. So we've got each one of these components. So let's look at access times. You got your registers, which is a negligible time. The CPU just bangs out. The L1 cache, though, it takes about 3 clock cycles. So it takes about 3 ticks to go into the chest, grab something, and bring it back. Getting to the fridge, though, your L2 cache would take about 20 clock cycles. So you could say he's like pulling a chicken out or something and it's got to thaw. Getting to the pantry is about 40 clock cycles. So the big thing here is your L1 cache and your L2 cache, each one of the cores can only access their own. So each one can only access their own chest and their own fridge. They're not allowed to grab from either of the others. The L3 cache, though, is a shared block of memory that any one of the cores can access. And then memory takes about 200 clock cycles. And it should be noted that these aren't exact numbers. They're approximate. They should only be used as kind of a reference of how long it should approximately take. And then even worse yet, you've got your hard drive, which could take 10 million plus clock cycles. And then if you're accessing the network, and that's even further out, that's a ridiculous amount of time for CPU. Okay, so we've got these access times. Now I want to show you why these access times even matter. So let's say that our chef wants to make green bean potato soup. So he's first going to look in his L1 cache. He's going to look in that chest and say, okay, I need green beans, but I don't have any in there yet. I haven't requested them before, so they're not there. And that's what's called a cache miss. Looks in there, not there, a miss. So the next step, he's going to look in his L2 cache. It's not in the L2 cache either. Okay, so the next step, he's going to look in the L3 cache, look in the pantry. No, still no green beans in the L3 cache. So there's another miss. So that means he's got to go all the way out to main memory. So that's where Farmer Joe's going to come in. Farmer Joe's been asked to get a green bean. And so he's got to bring this one green bean all the way back. But Farmer Joe's a little bit smarter than that. He's brought a basket. Okay, so Farmer Joe's got a basket that he's been asked to get one green bean, but typically you're not going to eat just a single green bean, you're going to eat a whole bunch of green beans. So he's going to intelligently grab a whole bunch of memory there, the green beans, and bring them over. It's called cache locality. The idea that if you're accessing one thing there, you can access a whole bunch of things, more than likely. So, now that he's got his green beans, he needs to bring them all the way back. And so this is the idea that once you get to main memory, you got to bring it all the way back through. And so now he's out to L3 cache. He brings it to the L3. Now he's going to bring it to the L2. And then finally he can bring it to L1, where the chef finally has his green bean. But he's making green bean potato soup and realizes, hey, I need potatoes. Okay, so he looks in the L1 cache, nothing. L2 cache, nothing. L3 cache, nothing. So that means that Farmer Joe has to go all the way back out to main memory again, so that then he can get potatoes. And that's a long journey. Okay, so Farmer Joe, he could do the exact same thing. He'd grab another row and pick all the potatoes and bring them all the way back. Well, let's say that we knew ahead of time that we were going to be making green bean potato soup, and we were going to be doing it a lot of times. And we could have thought ahead and instead planted a green bean and then a potato. Green bean, potato. That way when he picks up the entire row, he's got a green bean and a potato for every green bean potato soup that the chef wants to make. And so then when he picks it all up and brings it back, he's already got a potato already ready for the chef to use. And he doesn't even have to worry about requesting more from main memory. So this is the idea of data-oriented design. But it gets a little bit further. Let's say that we've got these sheep. And we want to add some lamb meat to this green bean potato soup. Now, a sheep is quite a bit bigger, and you could piece together your farm, so then you're planting a green bean, then a potato, and then you've got a sheep in its own little pen. and then you would grab all three things and bring them out and over. But let's say that this is our structure for our soup. We got our green bean, we got our potato, we've got our lamb. Now, instead of structuring it like this, which is the typical kind of almost OO type fashion, you just group everything together that's supposed to be related and then send it over. Instead, we could structure it like this. We've got soup vegetables, so you got your green bean, you got your potatoes, and then anytime that you need to work on green beans and potatoes, get those, bring them on the chef and chop them up, do whatever he needs to, and then you could process the lamb separately. And the lamb, typically you're going to want to cook it or do something different than what you would do for green beans and potatoes. And by doing that, you separate the two things, and then let's say a lamb is quite a bit bigger than what a green bean and a potato is. And when you look at your L1 cache is only 32 kilobytes. So we could say that each one of these vegetables are a single character byte. So you got 8 bytes total for each one of these vegetables. So it's 16 bytes. You can store a ton of these soup vegetables in that L1 cache. You can store 1,000 of these vegetables in the L1 cache and never have to go back to main memory. But if you included the lamb in that, say the lamb is 128 kilobytes or something like that, it's just a huge structured thing, you wouldn't be able to access the soup vegetables nearly as often as you could the soup meat. And so by separating them, you can process all those vegetables really, really fast, and then process the lamb really, really fast, and then merge the two together to create your soup. And so that's really the concept of data-oriented design, is trying to work with the data, the ones and zeros, to process them through the CPU and work with the memory so then you don't get quite as many cache misses. So here's a couple of things to check out. There's a Handmade Hero is a YouTube Twitch stream that is going on right now that he's building a game out right from scratch, going real low level. But something really good to check out that kind of relates to a lot of this stuff. Mike Acton, he recently did a talk at C++Con 2014 about data-oriented design. He does a really good job of covering this all, especially in a lot lower level detail instead of such high level here. And another one that I found interesting was Jonathan Blow's new language that he's working on. He's been doing a lot of Twitch streams here lately too that really help take advantage of this data-oriented design approach, and it's something to check out. So thank you guys for listening, and see you later.